After understanding the modern structure of the atom, it is important to learn how scientists gradually developed our present understanding of atomic structure. The idea of the atom did not appear overnight. It evolved over hundreds of years through experiments and scientific discoveries. One of the first modern scientific models of the atom was proposed by the English chemist John Dalton in 1803. His model, known as Dalton's Atomic Model or the solid sphere model, was the first scientific theory to explain the nature of matter using experimental evidence. Although some parts of Dalton's model were later proven incorrect, his work laid the foundation of modern chemistry and marked the beginning of atomic theory. Before Dalton, the idea that matter is made of tiny particles had already been suggested by ancient Greek philosophers such as Democritus around 400 BC. However, these ideas were based on philosophy rather than scientific experiments. There was no experimental proof to support them. John Dalton was the first scientist to develop an atomic theory based on observations, measurements, and laboratory experiments. His work transformed the concept of atoms from a philosophical idea into a scientific theory. John Dalton was studying the behavior of gases and chemical reactions when he noticed that elements always combine in fixed proportions to form compounds. For example, water always contains hydrogen and oxygen in a fixed ratio, regardless of where it is found. Similarly, carbon dioxide always contains carbon and oxygen in a definite proportion. Dalton realized that this regularity could be explained if matter were made of tiny indivisible particles called atoms. Using this idea, he proposed his atomic theory in 1803. According to Dalton's model, an atom is a small, solid, indivisible sphere. He imagined atoms as tiny, hard balls similar to miniature billiard balls. In his model, atoms had no internal structure. They contained no nucleus, no protons, no neutrons, and no electrons because these particles had not yet been discovered. Dalton believed that atoms were completely solid throughout, with no empty space inside them. One of the main ideas of Dalton's theory was that all matter is made up of atoms. Every substance, whether it is a solid, liquid, or gas, consists of countless tiny atoms. Although atoms are far too small to be seen with the naked eye, they are the basic building blocks of all matter. Everything around us, including air, water, rocks, plants, animals, and even our own bodies, is composed of atoms. Dalton also proposed that atoms cannot be divided, created, or destroyed. According to his theory, atoms were the smallest possible particles of matter. He believed they were indivisible and indestructible. During chemical reactions, atoms simply rearranged themselves to form new substances. They were neither created nor destroyed. Although this idea was later modified after the discovery of subatomic particles and nuclear reactions, it successfully explained many ordinary chemical reactions occurring under normal conditions. Another important part of Dalton's theory was that all atoms of the same element are identical. According to Dalton, every hydrogen atom was exactly the same as every other hydrogen atom. Likewise, every oxygen atom was identical to every other oxygen atom. He believed that atoms of a particular element had the same mass, size, and chemical properties. While this idea is mostly true regarding chemical behavior, modern science has shown that atoms of the same element can have different numbers of neutrons, producing isotopes with different masses. Dalton also stated that atoms of different elements are different from one another. Hydrogen atoms differ from oxygen atoms, carbon atoms differ from nitrogen atoms, and sodium atoms differ from chlorine atoms. Each element has its own unique type of atom with its own characteristic properties. Today we know that these differences arise mainly because each element has a different number of protons, known as the atomic number. Another important contribution of Dalton's theory was his explanation of how compounds are formed. He proposed that atoms combine in simple whole number ratios to form compounds. For example, one hydrogen atom combines with one chlorine atom to form hydrogen chloride, while two hydrogen atoms combine with one oxygen atom to form water. Dalton explained that atoms do not combine in random proportions, but always in fixed numerical ratios. This idea successfully explained the law of definite proportions, which states that a chemical compound always contains the same elements in the same ratio by mass. Dalton also explained that chemical reactions involve only the rearrangement of atoms. During a chemical reaction, atoms separate from one combination and join together in another combination. The atoms themselves remain unchanged. For example, when hydrogen reacts with oxygen to produce water, the hydrogen and oxygen atoms are simply rearranged into water molecules. This idea supports the law of conservation of mass, which states that matter is neither created nor destroyed during ordinary chemical reactions. Dalton's atomic theory was remarkably successful because it explained several important chemical laws that scientists had already discovered. It explained why elements combine in fixed proportions, why mass is conserved during reactions, and why different compounds have different compositions. His theory provided a logical framework that allowed chemistry to develop into a modern quantitative science. However, as science advanced, new experiments revealed several limitations of Dalton's model. The most important limitation was the discovery that atoms are not indivisible. In 1897, the English physicist Thomson discovered the electron through his cathode ray experiments. This proved that atoms contain smaller particles and therefore are divisible. Later, Ernest Rutherford discovered the atomic nucleus in 1911, showing that the atom has a dense central nucleus surrounded by mostly empty space. In 1932, James Chadwick discovered the neutron, completing our understanding of the three major subatomic particles. Modern science has also shown that Dalton's assumption that all atoms of the same element are identical is not completely correct. Elements often exist as isotopes, which have the same number of protons but different numbers of neutrons. For example, carbon-12, carbon-13, and carbon-14 are all atoms of carbon because each contains 6 protons. However, they have different masses because they contain different numbers of neutrons. Therefore, atoms of the same element are chemically similar but not always identical in mass. Dalton also believed that atoms could neither be created nor destroyed. Under ordinary chemical reactions, this statement remains essentially true. However, in nuclear reactions, atoms can be split, combined, or transformed into different elements. Nuclear fission, nuclear fusion, and radioactive decay all demonstrate that atoms are not completely indestructible. These discoveries were made many years after Dalton proposed his theory. Another limitation of Dalton's model was that it could not explain the existence of electrical charges, ions, chemical bonding, or electron configurations because electrons had not yet been discovered. It also could not explain why some elements are more reactive than others or why atoms emit light when heated. These phenomena were later explained by the discovery of electrons and the development of quantum mechanics. Even though several parts of Dalton's model were later revised, his theory remains one of the greatest achievements in the history of chemistry. He introduced the revolutionary idea that matter consists of atoms and that chemical reactions involve the rearrangement of these atoms. Nearly every modern concept in chemistry, including atomic number, mass number, electron configuration, isotopes, ions, and chemical bonding, builds upon the foundation established by Dalton. Dalton's model is often called the solid sphere model because he imagined atoms as tiny, solid, indivisible spheres with no internal structure. Today, we know that atoms are much more complex. Modern atomic theory shows that atoms consist of a tiny nucleus containing protons and neutrons, surrounded by electrons occupying different energy levels and orbitals. Most of the volume of an atom is actually empty space, a fact discovered through Rutherford's gold foil experiment. A useful way to compare Dalton's model with the modern atomic model is to think of a solid rubber ball and a miniature solar system. Dalton imagined the atom as a solid rubber ball with no internal parts. Modern science, however, describes the atom as having a tiny, dense nucleus at the center with electrons moving in regions around it, making the atom mostly empty space rather than solid throughout. So, always remember the main ideas of Dalton's atomic model. Atoms are tiny solid spheres. Atoms are the basic building blocks of all matter. Atoms cannot be divided, created, or destroyed during ordinary chemical reactions. Atoms of the same element are chemically similar, while atoms of different elements are different. Atoms combine in simple whole number ratios to form compounds. Chemical reactions involve the rearrangement of atoms. You should also remember its major limitations. Atoms are divisible because they contain electrons, protons, and neutrons. Atoms have an internal structure consisting of a nucleus and electrons. Atoms of the same element can have different masses due to isotopes. Atoms can undergo nuclear reactions in which they are transformed or split. Dalton's atomic theory marks the beginning of modern atomic science, although later discoveries improved and corrected several of his ideas. His model was the first scientific explanation of matter based on experimental evidence. It laid the foundation for all future atomic models, including Thomson's Plum pudding model, Rutherford's nuclear model, Bohr's planetary model, and the modern quantum mechanical model, making it one of the most important milestones in the history of chemistry. After Dalton proposed that atoms were indivisible solid spheres, scientists continued performing experiments to understand the true nature of the atom. One of the greatest breakthroughs came from the English physicist Sir Joseph John Thomson, commonly known as J.J. Thomson, in 1897 while performing experiments with cathode rays. Thomson made a revolutionary discovery that completely changed our understanding of the atom. He discovered the electron, the first subatomic particle ever identified. This discovery proved for the first time that atoms are not indivisible, as Dalton had believed. Instead, atoms contain smaller particles within them. Based on this discovery, Thomson proposed a new atomic model, which became known as the Plum pudding model. Before Thomson's experiments, scientists believed that atoms were solid, indivisible particles with no internal structure. Dalton's model explained many chemical laws, but it could not explain electrical phenomena such as electricity, electric currents, or the existence of charged particles. Thomson wanted to investigate the behavior of electricity in gases, and his experiments eventually led him to discover the electron. Thomson used a device called a cathode ray tube, which was a sealed glass tube containing a gas at very low pressure. Two metal electrodes were placed at opposite ends of the tube. When a very high voltage was applied across these electrodes, mysterious rays traveled from the negative electrode, called the cathode, toward the positive electrode, called the anode. These rays were known as cathode rays. Thomson carefully studied the behavior of these cathode rays. He observed that the rays traveled in straight lines, produced shadows, caused certain materials to glow, and could rotate small paddle wheels, indicating that they possessed mass and momentum. Most importantly, when he placed electric and magnetic fields near the path of the rays, they were deflected toward the positively charged plate. This showed that the particles making up the rays carried a negative electrical charge. After many experiments, Thomson concluded that cathode rays were actually streams of tiny, negatively charged particles. These particles were much smaller than atoms and were present in every type of material he tested. He called these particles electrons. Since electrons were found in all atoms, Thomson concluded that all atoms contain electrons. This was the first evidence that atoms have an internal structure. The discovery of the electron forced Thomson to develop a new atomic model. He knew that atoms are electrically neutral, meaning they have no overall charge. Since electrons carry a negative charge, there must also be positive charge somewhere inside the atom to balance the negative charge. However, Because the nucleus had not yet been discovered, Thomson imagined that the positive charge was spread uniformly throughout the entire atom. According to Thomson's Plum pudding model, the atom is a uniform sphere of positive charge, with negatively charged electrons embedded throughout it. He imagined the atom as a soft, positively charged ball in which electrons were scattered like small particles throughout the positive material. To help explain this idea, Thomson used the example of a traditional plum pudding, a popular English dessert. In this dessert, sweet raisins or plums are distributed throughout a soft pudding. In Thomson's analogy, the positive sphere represented the pudding, while the electrons represented the raisins scattered throughout it. This is why the model became known as the Plum pudding model. According to Thomson's model, the positive charge filled the entire volume of the atom. The electrons were embedded inside this positively charged sphere at different locations. The total positive charge exactly balanced the total negative charge of the electrons, making the atom electrically neutral. Unlike the modern atomic model, Thomson's atom had no nucleus. The positive charge was not concentrated at the center, but was spread uniformly throughout the atom. The main ideas of Thomson's model can be summarized as follows. First, atoms contain tiny negatively charged electrons. Second, the atom is a sphere of uniformly distributed positive charge. Third, electrons are embedded throughout this positive sphere. Fourth, the positive and negative charges balance each other, making the atom electrically neutral. Finally, the atom has an internal structure rather than being a completely solid and indivisible particle. Thomson's model was an enormous improvement over Dalton's model, because it successfully explained the existence of electrons and the electrical neutrality of atoms. Dalton had assumed that atoms contained no smaller particles, but Thomson demonstrated experimentally that electrons exist inside atoms. His model was the first to recognize that atoms possess internal structure. The Plum pudding model also helped explain why atoms can conduct electricity under certain conditions. Since electrons are negatively charged and can move under the influence of electric fields, they can carry electric current. This idea eventually became the basis for understanding electrical conduction in metals and many other materials. However, although Thomson's model represented a major scientific advance, it also had several important limitations. The biggest weakness was that it did not contain a nucleus. Thomson assumed that the positive charge was spread evenly throughout the atom, but later experiments showed that this was not true. In 1909, Ernest Rutherford and his students Hans Geiger and Ernest Marsden performed the famous gold foil experiment. They directed a beam of positively charged alpha particles toward a very thin sheet of gold foil. According to Thomson's model, the alpha particles should have passed almost straight through the atom because the positive charge was spread uniformly throughout it. Most of the alpha particles did indeed pass straight through the foil. However, to everyone's surprise, a small number were deflected through very large angles, and a few even bounced back toward the source. This result could not be explained by Thomson's Plum pudding model. Rutherford concluded that almost all the positive charge and nearly all the mass of the atom must be concentrated in a tiny, dense central nucleus, while most of the atom consists of empty space. This discovery completely replaced Thomson's model and led to the development of the nuclear model of the atom. Another limitation of Thomson's model was that it could not explain the arrangement of electrons within the atom. It did not describe electron shells, energy levels, or electron configurations. It also failed to explain why atoms emit characteristic spectra when heated or excited. These phenomena were later explained by Niels Bohr's atomic model and, eventually, by the quantum mechanical model. Thomson's model also could not explain chemical bonding, valence electrons, or why different elements exhibit different chemical properties. Although it recognized the existence of electrons, it did not explain how electrons were organized or how they participated in chemical reactions. Despite these limitations, Thomson's contribution to science was revolutionary. The discovery of the electron completely transformed atomic theory. It demonstrated that atoms are divisible and contain smaller particles. His work opened the door to modern atomic physics and inspired many future discoveries, including Rutherford's nucleus, Bohr's electron shells, Chadwick's neutron, and the development of quantum mechanics. Today we know that Thomson's picture of the atom is not correct. Modern atomic theory describes the atom as consisting of a small, dense nucleus containing protons and neutrons, with electrons occupying specific energy levels and orbitals around the nucleus. The positive charge is concentrated entirely within the nucleus rather than spread throughout the atom. Most of the volume of the atom is actually empty space. A useful way to compare Dalton's model, Thomson's model, and the modern atomic model is to imagine three different objects. Dalton imagined the atom as a solid billiard ball with no internal structure. Thomson imagined it as a plum pudding where tiny electrons are scattered throughout a positively charged sphere. Modern science, however, describes the atom as a miniature planetary system in which a tiny nucleus lies at the center while electrons occupy specific regions of space called orbitals. So, always remember the main ideas of J.J., Thomson's plum pudding model. Thomson discovered the electron through cathode ray experiments. Atoms contain tiny negatively charged electrons. The atom is a uniformly positively charged sphere. Electrons are embedded throughout the positive sphere like raisins in a plum pudding. The positive and negative charges balance each other, making the atom electrically neutral. You should also remember its major limitations. The model did not include a nucleus. It assumed the positive charge was spread uniformly throughout the atom. It could not explain Rutherford's gold foil experiment. It could not explain electron arrangements, atomic spectra, or chemical bonding. Even though Thomson's plum pudding model was eventually replaced, it remains one of the most important milestones in the history of chemistry. It was the first atomic model to include subatomic particles, proving that atoms have an internal structure. This discovery marked the transition from Dalton's simple solid sphere to the more sophisticated atomic models developed by Rutherford, Bohr, and modern quantum mechanics, bringing scientists much closer to our present understanding of the atom.